So, good evening, all. Good evening to the last live interaction session for this course, Waste to Energy Conversion. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, I think we can start our session. So I hope I'm audible and my presentation is visible. So I welcome you all to the last live interaction session for this course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering IIT Guwahati. I am one of the course team members. I am responsible for conducting the live interaction session for this course Waste to Energy Conversion in the Jan to May 2026 semester. So as I said, today is our last live interaction session. So we have seen across all the 8 live interaction session, our major focus was on how to extract energy from the waste materials, and I hope we did a reasonable job in understanding those fundamental concepts and principle, and we have also solved some of the problems. So we were left out with a few bunch of problems which were not solved due to time constraint or other issues in the or during the 8 weeks. So let us finish. Yeah. Okay. Actually, once the deadline is over, you cannot um, submit. You have to actually mail this to this NPTEL office, because I am not sure. As far as I know, you cannot submit the assignments after its deadline is over. Oh. Problem, your scores will, they will not, like, your scores will the scores will be less because you, since you didn't submit. Apart from that, nothing much. Oh, okay. So we have seen, I mean, yeah, so we have solved a decent number of problems, and since we were unable to solve a few of the questions, so I thought this would be a perfect time to finish those and wrap up the course for this semester. So let's jump directly into the questions without wasting any further time. So the biomass, so the first question is, the biomass productivity can be calculated using which of the following formulas among the four options? Here, Y2 and Y1 represent for the biomass concentration, and T2 and T1 represents for the time that is required to obtain that biomass concentration. So, how do you define biomass productivity? Among the four options that you have, let me just come out of the full screen mode. I hope this would be much clear. Answers. It's quite it's very simple actually. Anyone? You can just tell this as which of the following option. Is it the first, second, third, or fourth? So I have not given any numerals like A, B, C, or D. You can just tell whether is it the first option, second option, third option, or fourth option. So productivity by means, what we understand is how much amount of biomass has been produced within a certain time interval. C. Okay. Let me just check. Yes. So the option is option C. The correct answer is option C. Okay. So for this, so it is basically the difference in the biomass concentration, that is what is the excess of biomass that has been produced within the time interval of t to t1. So if you initially start at t equal to 0, if you have 0 amount of biomass that is produced, let's take a situation where at t equal to 0 the biomass concentration is 0, and after some time, let's say 1 hour, the biomass concentration increases to, let's say, uh, 1 kg or 2 kg. Then the difference, then the biomass productivity will be defined as 2 by whatever the amount of biomass that has been produced divided by the amount of time taken for the biomass to be produced. So that's what is defined as biomass productivity. So the option is option 3, y2 minus y1, that is how much amount of biomass concentration has been added in the time interval t2 to t1. So option 3 is correct. Next, I hope no doubts related to this question. So next question is, interrupting carbon dioxide supply to an algae system can cause microalgae to flocculate on its own, which is known as chemical flocculation, physical flocculation, autoflocculation, and manual flocculation. C. It is autoflocculation. Okay. So apart from that, what are the other types of flocculation that is there for this microalgae to flocculate? I mean, autoflocculation is one where you actually cut off the carbon dioxide supply. So once that CO2 supply to the microalgae is stopped, then they try to flocculate on its own and then settle down as flocks or flakes, and then they can be removed. But apart from this autoflocculation, there are also other types of algae concentration techniques are there. So what are those other techniques which can be used to concentrate these microalgae? Apart from flocculation, there are several other methods that you can use to concentrate the microalgae. So what are those other techniques? And I hope everybody knows this chemical flocculation we discussed in the last live interaction session. That was yesterday. So, what are the kinds of chemicals that we can add for this chemical flocculation to happen? There are two types of chemical reagents that we discussed in the last session. Two chemical flocculants. Anyone? Two chemical reagents or two chemical flocculants. One is ferric chloride FeCl3, another one is it has some chemical formula K2SO4 dot Al2SO4 thrice dot 24H2O. It's also known as alum and ferric chloride. Yes. So this is called alum. Okay. And so this is one thing. So apart from autoflocculation, there are also two different other types of flocculation techniques are there. And apart from this flocculation as such, we also have other kinds of techniques that you can use to concentrate this microalgae. What are those? So basically the summary session's main focus or main idea is to make sure that we can recollect what we did in the last 8 sessions. So it may be difficult for us to discuss all the concepts that we discussed throughout the 8 weeks. So through these kind of questions we can try our best to bring or to refresh the memory, to refresh our memory on what we have learned throughout the 8 weeks. So that is the main goal. And that is one of the main reason why it is kept on the very next day of completing the week 8 course or the 8th week of that course. So people will still remember much of the things so that it will be easy for you to, it's just about refreshing some of the concepts here and there, so that will be much easier for everyone. So apart from autoflocculation, what are the other kinds of techniques which is used to concentrate this microalgae? So one thing is called perkinetic flocculation, and another one thing is called as orthokinetic flocculation. So what's the difference between perkinetic and orthokinetic? It's just that the mechanism is different. And apart from these, you have sedimentation, and then the other two ways is centrifugation and ultrasonic. So what's the difference between perkinetic flocculation and ultrasonic agitation? Oh, sorry. What is the difference between perkinetic flocculation and orthokinetic flocculation? So, in case of perkinetic flocculation, the movement is usually governed by, or you can say the flocculation is mainly governed by the Brownian motion, that is the random motion of this microalgae. Whereas in case of orthokinetic flocculation, we there is a bulk motion, and that is usually created by stirring the fluid with the by stirring the fluid. So you try to stir the fluid so that you can create a bulk motion, and that bulk motion actually helps in flocculating the algae. And centrifugation and ultrasonic agitation, I hope you will be able to get it easily. So among both the centrifugation, you use centrifugal force to make sure that the algae get deposited, and in ultrasonic agitation you use ultrasonic waves to concentrate these microalgae. Since we use ultrasonic waves to concentrate the microalgae, the concentration percentage what we will recover will be more or will be greater. So that is the main advantage of that. Whereas in case of centrifugation, it's just a centrifugal force, so that may not be able to give as high algae concentration as that of the ultrasonic agitation. So shall we progress towards the next question? If you have anything to ask, please let me know, or otherwise we can progress forward. So let's just move forward. Match the following. So you have totally 7 elements in column A and 8 elements in column B. You are supposed to match column A to column B. So it will be either way. So for example, column A may have the equipment or the physical property, and column B will have their respective physical property or the equipment that is used to measure the properties mentioned in column A. So it's jumbled. So you need to tell which element of column A matches with the which element of column B. Please remember, you have totally 8 elements in column B, whereas 7 elements in column A. Anyone? You can either let me know one by one all the, I mean, the options one by one, which column matches with which one, or probably you can tell all the answer in one go. So in column A you have gravimetric or conductivity meter. In column B you have in column, and the next one is color. So color is a physical property, and that is usually measured by one of the following instruments that is there in column B. So you need to match which instrument measures color. And then you have pH meter, so that will be used to determine some physical property which is going to be there in column B. After that you have TSS, I hope everybody remember and knows what is TSS. Then you have trace metal. After trace metal, you have chemical method slash spectrometer, and then you have Beer Lombard's law. Let me delete this option for the time. So what will be the answer for or which option in column B matches with the element 1 in column A? Gravimetric or conductivity meter is used to measure which of the following physical properties mentioned in column B? Is it turbidity meter, alkalinity, inorganic substances, spectrophotometer, AAS, or total suspended solid, or TDS, or ICPMS? Yes, anyone, at least for the first one? One is G. Okay. Then second one, color. The color is usually something that is related to the wavelength of the molecules that is present in them. So so you can also rephrase this question as, instead of asking color is measured by which of the following instrument, I can say the the wavelength corresponding to a particular color is measured by which of the following instrument among the options in column B. So in the visible region of color, I hope all of you guys know that each color is represented by a certain wavelength. So now the question is, which instrument measures the wave? Which instrument measures these wavelength? Is it turbidity meter or spectrophotometer or alkalinity or inorganic substances or TDS or TSS or ICPMS or AAS? 2, somebody says it is E. Okay. Actually, how many of them here knows what is AAS? What is AAS? So AAS is nothing but atomic absorption spectroscopy. So 2, color is usually measured by a spectrophotometer. So option 2 corresponds to the element D in column B. So spectrophotometer is the one that is useful for measuring which wavelength of light is, I mean, which one of the in which, I mean, sorry, spectrophotometer is basically used to characterize that wavelength, and once we know which wavelength it is, then we will be able to see what color it actually represents. So 2 is D. Now 3, pH meter. What does pH meter measure? 3B. Okay, yes, 3B. pH meter measures the alkalinity. It's basically used to measure the pH. So alkalinity basically means that it is used to measure the how alkaline a system is. So anything beyond pH of 7 we call the system to be alkaline. So pH meter is used to measure alkalinity. 4, TSS, that is total suspended solid, is measured by which of the following instrument? Somebody says F. Okay. Actually, it is my mistake. TSS, actually, it should remain as an abbreviation. I told out the answer first itself. So 4 is TSS. So TSS full form is total suspended solids. So that is F. And apart from that, there is one more option. It's actually a multi-choice match. So each of the element in column A may match to one or more than one elements of column B. So that's the reason you have 8 options in column B, whereas only 7 in column A. Apart from F, there is another one more option which corresponds to TSS. A, yes. So TSS means total suspended solids, but it is usually measured by a turbidity meter. So how turbid a system is can be measured by a turbidity meter, and that how turbid it is basically gives us the information about how much solids are usually suspended within the system. Next we have fifth one, that is trace metals. Elements that are present in very minor quantities. HNE. So one thing is AAS, atomic absorption spectroscopy, and another thing is ICP-MS. Full form for ICP-MS, anyone who knows the full form? It is the inductive coupled plasma mass spectrometry. So here you use plasma, and then by using the plasma you basically excite the electrons, and using a mass spectrometer you determine which element is present and how much and what is their concentration. So usually the percentage of elements that these ICP-MS or AAS usually measures will be in the order of ppm to ppb. Also it can usually measure. So ICP-MS can measure up to ppb concentration or even less. So how accurately you can measure this trace metals? For accurate measurement of these trace metals which are present in very minor quantity, you can use AAS, atomic absorption spectroscopy, or ICP-MS, inductive coupled plasma mass spectrometry. Then sixth one, chemical method slash spectrometer. Six is D. Six should be uh, isn't six, the option 6 should correspond to C, chemical method slash spectrometer for measuring the inorganic substances. I say 6 should be C. Is it fine or any confusion on why? I mean, why option D actually? Someone said option D. Okay, somebody's now telling 7 is D. Yes, 7 is D. And there is one more which follows Beer-Lambert's law. One more instrument. In your AAS, atomic absorption spectroscopy can also measure Beer-Lambert's, sorry, atomic absorption spectroscopy or equipment also uses Beer-Lambert's law as its working principle. So now the question is, what is this Beer-Lambert's law? Any brief statement? What is Beer-Lambert's law? What is Beer-Lambert's law? Anyone? So if you don't know, try to look at that. Look at this. What is Beer-Lambert's law? So this is the major working principle behind the spectrophotometer as well as the AAS, atomic absorption spectroscopy. But we need to know what exactly this Beer-Lambert's law is. So if you know, then you are welcome to let me know. Or in case if you don't know, then kindly have a look at it after the session gets over. So is there any question related to this match the following? Because this is a multi-choice match. Here, I wantedly came up with this example so that it will be, it's something more like how they used to do it in this competitive exams like GATE. So they often prefer phrasing questions like this, where one option of one column can match with multiple options in another column. So if you have any questions, then you can let me know, or I think if not, then we can progress towards the next one. Okay, so I hope no questions. Absorption of light is proportional to concentration, and there is another one more proportionality. Absorption of light is proportional to concentration, and another one more physical quantity, which is the optical length. So optical path length. So absorption of light is proportional to concentration and the optical path length, and the proportionality constant is called as molar extension coefficient. So this is the Beer-Lambert's law. So yes, if no doubts related to this match, then I think we can go to the next one. This is a simple one. Ethanol yield can be calculated by which of the following expression? Where C is the ethanol concentration, V is the initial volume of liquid, M is the mass of substrate. I think this is also one of the assignment questions of this year. So I just wantedly came up because these factors will be maybe quite important. CV by M or MC by V or V by C, or other option was none of this, but I deleted that. Option A, CV by M. So what is the definition of ethanol yield? The formula is CV by M, but it has a what do you say, definition, right? So kindly have a look at the definition as well. So let's move on towards the next question. Oh, we have totally 5 more MCQs to finish. Okay. Which routes have relatively slower rate of energy production from waste? Biomass, I mean waste as in biomass and municipal solid waste material. Is it thermal or biological or chemical or none of these? Slow rate of energy production. So the rate at which your energy is going to be produced is going to be very slow. It's not going to be rapid. So a long time will take to produce the same amount of energy compared to other techniques that is used for energy production. Is it biological, thermochemical, chemical, or none of this? So when you answer, so it is option A, biological routes. They have very slow rate of energy production. Then let's come to next question. Determine the stoichiometric air that is required to combust the methane. So how much amount of air will be required to combust 1 gram of methane? We have solved this kind of questions, so take some time 2 to 3 minutes, and then let's discuss the answer for this one. So keep solving. I will be just. Oh no. So first you need to write the combustion equation for methane in the presence of air. Once you do that, then you need to do the stoichiometric calculations to find out how much air is required to burn 1 gram of methane. So just a second. So any answers? Okay, let me write the conversion equation first, then I think it would be better. So methane is CH4 plus, here it is written how much air we require. So I hope all of you remember that we cannot neglect nitrogen being present. So it will be O2 plus N2 gives CO2 plus H2O. I hope the equation is correct. Anything that I'm making mistake? Nitrogen gas is going to be inert, so that is not going to react actually with your CH4. So that entire nitrogen gas will actually come out. So that is N2 is inert in nature. So that will be there in the product stream as well. So now we need to balance this reaction, right? So I hope all of you remember that for every 1 mole of O2, we have totally 3.76 moles of nitrogen. We already did this kind of, what do you say? They, we did already this calculation before in our second or third live interaction session, if I'm not wrong. So I hope all of you remember how we did that. So the concept was, in air we consider that there is 79 percentage of nitrogen and 21 percentage of oxygen, and we assume that the other gases do not contribute significantly to the composition, so we neglect their contribution and we assume that air is predominantly composed of only nitrogen and oxygen, which is 79 percentage and 21 percentage. So we assume that for 1 mole of air you will have 0.79 moles of nitrogen, 0.21 moles of oxygen. So then we calculated that for 1 mole of oxygen how much mole of nitrogen is going to be present, and then we got the value as 3.76. So I hope all of you remember that. So as we now know that nitrogen is going to come out as inert, so that will be like let me write it this way. So since we do not know the stoichiometric coefficient, we are going to keep it as n. So we will, in the product stream, we will have 3.76 times n moles of nitrogen gas that will come out. So we now need to balance this equation. So if you see here, we have two hydrogen, so this will be 2, and then oxygen will be 4 oxygen. Yes, and carbon is 1, so this will be 4. So this value of n is 4, so nitrogen will be 3.76 times 4 moles of nitrogen will be present. So now our question is, for 1 mole of CH4, 4 moles of air is required. So for 1 gram of CH4, how many grams of air will be required? So we know that 1 mole of CH4 requires 4 moles of air. So for 1 gram of CH4, how many air is required? So we need to calculate the value of X. Any answers? Oh, we have an answer. Somebody says option D. Okay, let's see. So 1 mole is nothing, 1 mole of CH4 is 16 grams per mole, and 4 moles of air is, how much it would be? O2 plus 3.76 times of N2. O2 is 32 plus 3.76 times 28. 4 4 times 105.28. Okay. So for 1 gram, how much amount of air will be required? So that would be, so that would be 4 times 105.28 by 16. So that will be 105.28 by 4. It says 26.32, but we do not have an answer. Am I making some mistake somewhere? Oh, I made a mistake here. It should be 2 because we have 4 oxygen, so 2 to 4, so this should be 2. So that would be 105.28 by 8. I think we are making some mistake again. 32 plus 4 times, sorry, 3, 3.76 times 28. See, so 105.28 plus 32, 137.28. So 137.28 by 8, 17.16. So as somebody said, the answer is 17.16 gram of air for air per gram of CH4. So again, a small error in hindsight, and the entire answer was wrong. So that is the reason these kind of questions are important, because a small error in balancing this equation or not considering the nitrogen concentration into nitrogen, the presence of nitrogen into the equation will change the answer definitely. So if you are not going to take nitrogen under consideration, the 3.76 times 28, then the answer would be 2 times 32, that is 64. 64 by 16, that will be 4. So then it will be like 4 gram of oxygen is required for 1 gram of methane. But since we are asked to know what is the air requirement, it's going to be 17.16 gram of air per 1 gram of CH4. Any questions related to what we did in this one? This is a simple one. So if you remember, we solved a very more lengthy question based on the similar concept, where we discussed about stoichiometric quantity of air that is required. At the same time, we also brought in the concept of excess of air that is required for the combustion of some hydrocarbon. So if you have any doubts, you are welcome to let me know, or we can go to the next question. Which pyrolysis technology operates at a very high heating rate and residence time of less than zero point 0.5 seconds, producing mainly chemicals and gases? Is it slow pyrolysis or carbonization or ultra pyrolysis or vacuum pyrolysis? Of course, carbonization will not be there. So C option, ultra pyrolysis. So ultra pyrolysis is the one that has a very high heating rate and the entire residence time is less than 0.5 seconds. So if you go in case of slow pyrolysis or vacuum pyrolysis, the residence time will be more because their heating rate is low. Let's move on. These two are very simple questions. Which of the following electrocatalyst is used in microbial fuel cell? Is it graphite, naphthalene, polyaniline, or porcelain septum? And of course, you need to tell me apart from which of the following is an electrocatalyst in microbial fuel cell. The other options corresponds to which of the components in the or the other material corresponds to which of the following components of the microbial fuel cell. Option B. Okay. Please read the question carefully. It says which of the following is an electrocatalyst that is used in microbial fuel cell. Is naphthalene an electrocatalyst or does it belong to some other component? It should be polyaniline. Polyaniline is the electrocatalyst. Graphite is the electrode. Conventionally, in case of proton exchange membrane fuel cell, if you see, we use platinum or platinum supported carbon as an electrocatalyst. But again, these polyaniline and MnO2, they are all kind of the recent developments that you have that we can see in the microbial fuel cells as electrocatalysts. Naphthalene will be the membrane, polymer membrane, and porcelain septum is ceramic membrane. So these membranes are responsible for the transfer of protons from the anodic chamber to the cathodic chamber. So in case of that membranes are usually made of either polymer or ceramic. So if you have polymer, then it's Nafion. Nafion is actually a commercial name. The chemical name for Nafion is perfluorosulfonic acid membranes, PFSA. Or you can also use porcelain septum, which is a ceramic membrane. So let me write this. Nafion is commercial name. Chemical name is PFSA, or you can also say perfluorosulfonic acid membranes. So it typically has a PTFE backbone, PTFE backbone, and then you have SO3H groups in the form of side chains or pendant chains, what we call as. So kindly remember this, because microbial fuel cell is one of the important concepts. So that you may happen to have these questions in the exam. So I don't know. Next question: what are the three T's for complete combustion of solid waste? Is it time, temperature, turbulence, or time, temperature, tensile strength? I think this would one will be the easiest of all. Time, temperature, and turbulence. So you require time, sufficient time for the combustion, you require sufficient temperature for the combustion, and also you require sufficient turbulence for the combustion, so that the uh, sufficient oxygen is there for the combustion process to happen. So the three T's that is required for complete combustion is time, temperature, and turbulence. Tensile strength is usually a mechanical property of elastic materials, or you can say flexible materials. So that will not come with the combustion perspective by any chance. So it's time, temperature, and turbulence. So any questions so far in what we have discussed with the numerical, with the MCQs, multi choice questions? Any questions? If no questions are there, then I think we can go to the next, to the towards the problems. Anyone, any questions? So shall we progress towards the numerical problems? So we have approximately 50 minutes with us. So I hope that would be sufficient to finish our work. So let's see. So let me move towards the questions. So we have somebody raising something. When we get our hall tickets. Ma'am, actually, I'm not sure about that part of the, for the exam, when need you receive hall tickets. But what I can say is, it would be better if you directly mail the NPTEL office regarding this. So they will be able to guide you more properly than me. Just a second. Which question is okay? So let's start with this one itself. So simple ones. I hope the time will be sufficient to complete all of them. So during the pre-treatment, 60% of the lignocellulosic waste, the biomass, is going to be converted to monosaccharide and disaccharides in the mass ratio of 3 to 7. The monosaccharide produces 600 gram of ethanol per kg of monosaccharide, and the disaccharide produce 500 grams of ethanol per kg of disaccharides. Calculate the total yield of ethanol in kgs. So this may look like a very familiar question with what you have solved. As I said, this is a summary session, so this is for just for practicing, or you can also say refreshing what we have learned previously in the course. So some of us may tend to forget how to solve few problems. So for them, these questions will be, or this session will be extremely helpful. So kindly solve this and let me know the answer. Do we have an answer? Okay, no answer still now. Oh, 0.264 kgs. Okay, so okay, we have an answer. One answer is 0.264 kgs. Let us solve because I do not have the answer with me. I also need to solve it along with you guys. Then only I'll be able to know whether the answer is correct or not. So I'll just wait. So let's just wait for a minute or so. Then we will start solving the problem. So shall I start solving? Do we have any other answers? Oh, okay. Again, I mean, another answer is in kgs it is 31.48. Okay. So let's start solving. So it says that 60 percentage of the lignocellulosic waste is going to be converted to monosaccharide and disaccharide. So it's not that the entire biomass waste or lignocellulosic waste is going to get converted, but it's only 60 percentage of the mass of the lignocellulosic waste is going to get converted. So first let me take a basis as 100 kg of lignocellulosic waste. So basis is 100 kg of lignocellulosic waste. So if we have 100 kg of lignocellulosic waste, 60 percentage will be 60 kg of the waste is converted to, okay, is converted to mono and disaccharides. Now it is written that out of this 60 kg of waste which is going to get converted to monosaccharide and disaccharide, it is going to be converted in the ratio of 3 is to 7. So amount of monosaccharides is 3 by 10 times 60. So which is nothing but 3 times 6, which is 18 kg, and amount of disaccharides is going to be 7 by 10 times 60. So which would be 7 times 6, which is 42 kgs. Now we know that for 1 kg of monosaccharide we are going to get 600 gram of ethanol. So for 18 kg of monosaccharide we will get amount of ethanol from monosaccharides is 600 times 18, which is 18 times 600, 10,800 grams of ethanol. Now the same thing, amount of ethanol from disaccharides is, so for every kg of disaccharide you are going to get 500 gram of ethanol. So that would be 500 times 42, because we have 42 kgs of disaccharide. So that would be so 42 5 is 210 grams of ethanol. Now the question states that calculate the total yield. So total yield will be nothing but yield of ethanol from monosaccharides plus yield of ethanol from disaccharides. So that is going to be 10,800 plus 21,000. So that is going to be 800, 31,800 grams of ethanol. And since the question asks us to express it in terms of kg, so total yield of ethanol in kg is equal to 31.8 kg. So the total yield of ethanol is going to be 31.8 kgs. I think yes, this answer is correct. So it's very simple. It's just that we need to know that how to take the basis. You can take the basis as anything you want. You can even keep it as, instead of 100 kgs, you can even keep it as 1 kg and then progress. So that will not change the answer. Just to make sure that my calculation is easy, I kept the basis as 100 kg and assumed the 60 percentage of 100 is going to be 60. So that value is going to be far more easier for me, because if I'm going to assume it as 10, then I'm going to end up as 60 percentage of 10, that would be 0.6, right? So that would make my, wait, 60 percentage of 10 is 6, sorry, so 6, and then you need to take 3 by 10 of 6, that would be 1.8. So in order to avoid decimals, I took the basis as 100 kgs. So I hope no doubts in this question. Anyone, any doubts or anything that is confusing? If not, then I think I can go to the next question. Anyone, any queries, any questions? Okay. If no doubts, then let's see the next question. No, let's move on to, not this one. Oh, wait. Huh. This one. Next we will come to this, because this we have already solved. This is just a similar problem. So let's see this question. A fast pyrolysis plant handles 1 TPD MSW and produces gas, char and liquor. Operating temperature and pressure of the reactor is 788 degrees Celsius and 1 atmospheric pressure respectively. Gas composition is given as hydrogen is going to be 30.16, CO is going to be 39.5, CH4 is going to be 15.5 and CO2 is going to be 12.3. The mass percentage of production of gas, char and oil are 33, 25 and 42 respectively. Determine the product distribution with the individual component of gas and the rate of hydrogen production assuming 89% separation efficiency for hydrogen. So you are given a fast pyrolysis plant and you are also given how much waste it can handle, and it actually generates gas, char and liquor. You are given how much percentage of in the product stream, what is the percentage of gas, char, and coal, char and oil? That is 33, 25, and 42. So that makes up 100. Now, in this gas, you are also given what is the composition of the gas. Now, with these data, they are asking us to determine the product distribution with the individual component of gas and how much hydrogen will be produced, assuming 85% separation efficiency. So what is 1 TPD of municipal waste? Just a second. How many more questions? One, two, three. Okay. Tons per day. TPD means tons per day. So 1 TPD means 1 ton in 1 day or 1 ton per day. Just a second. I am extremely very sorry. Some disturbance. Later, I'm in a class. Right. Very sorry. So how to go about solving this particular problem? Any answers or any approaches? Anyone? Okay, so let's start solving the problem. I think it's already 5 minutes into the question. So the MSW handling rate is 1 ton per day. So this data is what we know, and we know that what is the operating temperature and pressure, but that let us keep it for some time. Yeah, the question is a bit lengthy one, but we need to solve that. I can understand that, but let's try solving the problem. Because if we suppose somehow run out of time, then we have few questions. Suppose let's hopefully we won't run out of time, but in case if we run out, then what I will do is I will post the answers while I upload the PPT. And since these models are same as what was discussed in the tutorials of the course content, so I hope it should not be a big task. But in case if you find any difficulties, then again, as I always say, you're welcome to email me. I will respond to that doubts as much as I mean, I will respond to that doubts on that. So, what's the next step? Once I have this municipal handling rate as 1 ton per day, we are given the mass percentage of gas, char, and oil. So, with that, we can calculate what will be the respective mass percentage of each of the components. So, mass of gas is going to be 330 kgs. Again, 1 ton is 1000 kgs. So, mass of char is 250 and mass of oil is 420 kgs. So this is their mass composition. Now, now what we are supposed to do next? At least if you can let me know the procedure, then it would be even easier, faster for us. What's the next step? So we know the gas composition by volume percentage. So we need to calculate actually the number of moles of gas that gets produced. So we can use that data and calculate the average molecular weight of the gas. So did anyone calculate what is the average molecular weight of the gas? So let me just calculate this quickly in my personal calculator. So what's the average molecular weight of gas? Anybody calculated that one? Oh. Yes, so the answer is coming out around 19.56 gram per mole. So once we know this average molecular weight, we can actually calculate the number of moles of gas. So gas produced per day. So 330 kgs of air is produced, 330 kgs of gas is produced per day. So the number of moles will be 330 by 19.56. So that is approximately 16.87 kilomoles. So this is in kgs. So and the denominator is in grams. So you need to multiply kilomoles of air per day. Now we know this. So based on this data, we need to calculate what will be the volume of hydrogen gas that gets produced. Is that correct? Anyone? Next step after this? Yeah, 16.87. But after this, the next step, we need to calculate the volume, right? Because till now we do not know the volume. Okay, yes, individual moles. So what would be the individual moles? So if since we are talking about H2, so moles of H2 is 0.3016 times 16.87 kilomoles obviously, so that would be 0.3016 times 16.87, so that is 5.087 kilomoles of H2. So we know that at STP conditions, standard temperature and pressure conditions, 1 mole of any uh, substance will occupy 22.4 liters. So based on this, we need to calculate how much 5.087 kilomoles is going to occupy. So let me just write that as well. Volume of H2 at STP, standard temperature pressure, is going to be 5.087 times 1000 times 22.4 liters. So that would be 5.087 times 22.4, 113.9488 88 meter cube. So 1 meter cube equals to 1000 liters. So the expression that I get in terms of liter, I am going to divide that with 1000 and express that in terms of meter cube. So this is the volume of H2 at STP. Now once you know this volume at STP, you need to calculate what will be its volume at 788 degrees Celsius, because that is the operating condition. So what it would be? So if you use ideal gas law, PV equals nRT, pressure will remain constant as 1 and 1, N will be same, R will be same, so the volume is going to depend only upon T. So V1 by V2 equals to T2 by, the volume that is occupied at 788 degrees Celsius by the volume at occupied at STP equals to equals to 788 degrees Celsius by 298 Kelvin, or you can say 25 degrees Celsius. So then the expression would be something like this: 113.9488. I'm expressing everything in terms of Kelvin. So 788 degrees Celsius will be plus 273. 1061 by 298. So what's this expression turning out to be? 1061 by 298 is 3.56 times 113.9488, 405.70 meter cube. Meter cube of H2 is produced. Now similarly you need to calculate, since they have asked for the product distribution with the individual component of gases, you need to do like this for every single component, that is carbon monoxide, methane and carbon dioxide. But here, since we are more interested towards knowing the rate of hydrogen production, so we will not calculate the other, but then the procedure remains the same. It is stated that 85% separation efficiency for hydrogen. So what will be the final answer? Volume of or hydrogen production is, or I'll put it as rate of hydrogen production equals to 3. Okay, just let me check once. 352.959. I think almost it is same. 52.9 meter cube, but here there is a catch. This is the amount of hydrogen that is going to be produced per day. So now if you want to actually estimate in terms of per hour, then you need to actually divide this with 24. So that would be 352.9 by 24. 14.7 meter cube per hour. I think someone stated 300 some value meter cube per hour, but that should be meter cube per day. Okay, that is STP conditions. We take temperature as 25 degrees Celsius. So Kelvin, it should be 273 plus 25, 298. So I think we cannot take temperature. We should not take temperature as 0 degrees Celsius. So kindly take care of that. And this answer should be 14.7 meter cube per hour, because we are taking the value in terms of uh, because everything over here the basis is in terms of days. So everything is here, it is in terms of days. So when you calculate or when you are going to represent your answer in terms of hour, kindly have a look at this. So any doubts with this question? So we have totally three more questions left out, but I think as per time constraint we will be able to solve one. So let's finish that one and then conclude our session today. The next two questions, which whenever is left out, I'll post the answers. I think probably we took a lot of time in the MCQs. But that is fine, because in the exam you will have more I mean, as like in assignments you will have lot of MCQs hopefully. So that I think it would be beneficial. I think it was beneficial for all of you. So any questions or queries or confusions in this one? Okay, so that's fine. Kindly take care of that conversion of days and hours, that units. Please check where before you mark the options in the exam. So any queries or any questions? So if there is no question, then let's check. Actually speaking, question this one, I mean the question 2, this question and this question is approximately the same. So let's do this one, and then I think we will be done. Only one question will be left out, so that's fine. I'll post the answers for that. In a high rate biogas plant, in a high rate biogas plant, food waste is anaerobically digested to produce biogas. The slurry contains 10% of solid food grains. Elemental composition is carbon is 60, hydrogen is 7, oxygen is 25, nitrogen is 8. Assume 80% of the food grain is going to be converted to biogas, and all the converted hydrogen forms methane. If the flow rate of slurry is 4000 liter per day, calculate the rate of biogas CO2 plus CH4 production. So you have a biogas plant, and that is doing anaerobic digestion in the, I mean, in the limited supply of oxygen or in the absence of oxygen. The slurry contains 10% of the solid food grains. Elemental composition is given in terms of carbon, hydrogen, oxygen and nitrogen, and it's in the percentage of mass basis. 80% of the food grains is converted to biogas, and all the converted hydrogen forms methane. If the flow rate of the slurry is going to be 400 liters per day. Calculate the rate of biogas produced. Oh, sorry, CO2 and CH4 together, the whatever that is produced, we are supposed to calculate that one. Sorry, we are supposed to calculate the rate of biogas, which is nothing but CO2 plus CH4 together. That production rate we are supposed to calculate. So how to go about this problem? You can, I think, wait a minute, just a second. Assume that the density of slurry is 1 kg per liter. Assume density of slurry as 1 kg per liter. So that would make the problem more easier. So we know the flow rate of slurry. So using density, you will be able to calculate what will be the amount of slurry. And it is written that 10 percentage of the slurry contains food grains. So once you know the amount of slurry, you can calculate what will be the solid food grains that is present. And based on that, you will be able to calculate the elemental composition, that is the carbon percentage, hydrogen, nitrogen and oxygen percentage. So once you know that, it is written that 80 percentage of the food grains is converted to biogas, and all the converted hydrogen forms methane. So now you are supposed to calculate the rate of biogas, CO2 plus CH4, the production rate. So how to start? So let me start solving. Oh. So density is 1 kg per liter. So that means, and if it is written that flow rate is 400 liter per day. So which means with this we can calculate what is the mass flow rate, and is nothing but density times this flow rate. So that will be 4,000 times 1, so that will be 4,000 kg of slurry per day. Now it is written that only 10%, it contains only 10 percentage of the solid food grain. So the mass of solid food grains is going to be zero point 0.1 times 4,000. So that is 400 kgs of solid food grain is present, and this solid food grain has this composition. So C is 60 percentage, so that would be 0.6 times 400, and hydrogen is 0.07 times 400, Oxygen is 0.25 times 400 and nitrogen is 0.08 times 400. So this would be 40 times 6, 240 kg. This would be 28 kg. This would be 25 times 400 kg, and this would be 8432 kgs. So this is the elemental composition of the food grain in terms of mass basis. Now it is written that 80 percentage of the food grain is converted to biogas and all the converted hydrogen forms methane. So if you write for carbon, because biogas main is composition is carbon, so out of that 240 kgs, 80%, I mean out of that 240 kgs of carbon that is present in the solid food grain, 80 percentage is converted to biogas, so that is zero point 0.8 times 240, and hydrogen is going to be also getting converted, so that would be same 0.8 times 28. So what would be the value? 24 times 8. 192 kg, and this would be zero point 0.8 times 28, 22.4 kgs. So this thing is done. After this, how we should progress? So it is written that, so we have calculated what will be the 80 percentage of that food grain is converted to biogas and all the converted hydrogen forms methane. So how to go after this? So it is CH4, right? And all the hydrogen, whatever we have here as 22.4 kgs is going to convert only to methane. So CH4, this thing is there, and what it typically means is, so 4 gram of hydrogen in 16 gram of methane. So then this entire hydrogen is going to get converted to methane only. So 22.4 kgs, all calculations are right? Okay. Will have how much amount of methane? So then that would be uh, of hydrogen will get converted to 16 times 22.4 by 4. So that is 22.4 times 4. 89.6 kgs of methane. Now this we have how much kg of methane will be there. Now once we know that, we need to calculate how much carbon dioxide will be produced. So can we do this calculation again? If 4 grams of hydrogen gives 16 gram, I mean if 16 gram of methane has 4 grams of hydrogen, then how much amount of carbon will be there? 12. So I'll put this in the other way. So 12 grams of carbon in 16 gram of methane. So how much will this 89.6 kg of methane will have? 89.6 kg of methane will have how much carbon? So that would be 89.6 times 12 by 16. That would be 89.67.2. Carbon will be there in 89.6 kg of methane. Now we know that the total carbon that will be converted to biogas is 192. So carbon left is 192 minus 67.2, which is 190 124.8 kg of carbon. Now we know that this much carbon is left out, and these are going to get converted to carbon dioxide. So again, same way of calculating. So 12 gram of carbon in 44 gram of carbon dioxide. So 124.8 or 124.8 kg of carbon will give how much CO2? So that would be 124.8 times 44 by 12. 124.8 times 44 divided by 12. 457.6 kgs of CO2 will be produced. So now we are asked what will be the rate of biogas production, CO2 plus CH4. So that would be 457.6 plus 89.6. So which is equal to 457.6 plus 89.6. 547.2 kg per day. So again, if you are asked to express it in terms of hours or seconds, kindly convert that kg per day to kg per hour or kg per minute or kg per second. So this is how you calculate the rate of production of the biogas, that is CO2 plus CH4 production. If you happen to see this question, here we ask only calculate the amount of methane produced per day. So in this you don't need to take the extra burden to calculate the CO2 content. So that's just the difference between these two questions. It's exactly the same. Over here we are asked to calculate CO2 plus CH4. Here we are just asked to calculate the methane. So anyone came up with the answer? Okay, okay, that's fine. I think I'm going paid to into people's dinner time, so sorry for that. Any questions? This question is left out, so I will post a slide by today or tomorrow related to how to solve this problem step by step. And I think this question is also solved in your tutorial, so this should, I hope that there won't be any difficulty, but in case if you have, you're welcome to email me. Sorry that I was not able to complete that question. So any questions so far, anyone, related to what we have discussed today? Let me just stop presenting. Ah, stop sharing. Yeah. Yeah, okay. So if anyone has any questions, then you're welcome to let me know, or otherwise we can conclude our session. So, okay, so I don't want to take much of your time. So let me just conclude our session for today. So I thank everyone for joining today's live interaction session, and all those who have been joining all these live interaction session for the past 8 weeks. So I hope this course was useful to you, and I hope you are able to get more than what you have expected from this course. So thank you all for joining these sessions, and all the recorded sessions will be uploaded, including along with their presentation, so you can access them by tomorrow. So I thank Professor Prasenjit Mondal sir for providing, and the NPTEL team for providing me this opportunity to interact with you all throughout this course. So thank you so much, and let's meet somewhere in some other course. So till then, thank you. Have a great week ahead, and all the best for your future, as well as all the best for the NPTEL exam. So yeah, thank you so much once again, and bye.